Hello there, it's exercise 6A, which is discrete maths again for further maths. And I need to start off, I suppose, by just reminding you of what we did at GCSE on this topic and then extending it. And actually, this question here, which I've got a picture of, this would be an A-level version of what a topic that you saw at GCSE. So let me just go through what we do at GCSE, and you should remember this. You typically got asked to shade a region given by some inequality. So for instance, and these are fairly random, aren't they? It says shade a region satisfied by the inequalities, and you'll notice it says -4 is less than or equal to y is less than 2. Now, essentially that means y is between these two numbers. And since this is the y-axis, you should remember, look, there's 2 there and there's -4 there. So in actual fact here, what I've been asked to do is I'm being asked to shade in the region that's in between y is equal to 2, which is this line here, and y is equal to -4. Well, it's not quite like that. For a start, this y is not allowed to be equal to 2. So we show that with a dotted line going horizontally across. Because it's the y-axis, where does it hit? Where does y equal 2? And because it's not allowed to actually equal 2, I don't draw a full line, I just draw this dotted line. It's also got to be more than -4. So I draw, now this time I'm actually going to draw a proper thick line. And I'm drawing a thick line because here it is actually allowed to be equal to the -4. So where's the region where where y is between these two numbers? Well, this is the region. And typically at GCSE you had to shade in areas like that. What does the second one look like? It says y is greater than or equal to x. Y is more than x, essentially. So what we need to do, and this is all about, do we know the equation for the line y equals x? If you know the equation for the line without the inequality, then you can worry about shading it. So y equals x is actually where there, that's the proper 0, 0. I don't think my lines are quite in line, but you get the idea. And that's 0, 0. This is 2, 2. Basically, it's a series of points where y is equal to x. That's 4, 4. This is 6, 6, etc. Oh, this one's -2, -2. So when is it equal to x? That's the line. Allow for my slightly dodgy ski width line. That's the line y equals x. Now I want to shade the inequality where y is more than x. So in other words, any y value is greater than the x value. And just a bit of common sense really says it's the bit above the line. So there is my region. And this bit over here as well, but y is greater than x or equal to x. And notice because it was equal to, I drew a proper solid line rather than a dotted line. So that's what happened at GCSE. That's the kind of thing we saw at GCSE. Now, what's different then about A-level? Well, for a start, we call it feasible regions and linear programming. And I suppose the major difference for me is you're going to get more than one of these to shade at a time. So the way we deal with that is we end up shading the bit that we don't want, which seems a bit bizarre. By that, essentially, and that question just now where I had y is greater than x, I might have also had I had y is greater than or equal to x, and I also had that statement that y was between -4 and 2. I think it was 2. And that one was kind of a dotted line going across here and a line going across here. Now, if I was to shade in the bits I want, you quickly realize it gets very messy. So it's actually better to shade in the bits you don't want. So I don't want the bit underneath this diagonal line, and I don't want the bits on the outside of this now. I wanted the bits to be between it, so I don't want the bits on the outside. And you can see there is this bit over here which is unshaded. And usually we put a big capital R to represent the region that we want. And by doing it that way, it tends to work better. So just be aware that inequalities are usually called constraints because they're all to do with real life problems, and you have constraints in real life problems, like how many workers you have for a job, or how many grams of cheese you have when making a pizza, or something like this. So constraints are effectively inequalities. And just remember, we're going to draw these graphs, but do try to remember, shade the bit that you do not want, and then just put a big capital R for the bit that you do want, it's left over. So let's do a question, and you'll soon get to your grips with this, I hope. Identify the feasible region given by these constraints. Well, first of all, you need to know what y equals 12 minus 2x looks like. And you should remember it crosses at 12. Well, that makes it a bit tricky. It crosses up here somewhere. So what am I going to do? Well, I've got to get a couple of points. Well, I could substitute 2 into this. If I substitute 2 into this, x is 2. And that quickly becomes 4. 12 minus, that's 8. So 1 point quickly. And you can do all this in your head. You don't need to do it neatly. And what about when x is, I don't know, pick a different point. X is 6. I picked 6 deliberately because 2 6s are 12. 12 minus 12 is 0. So that, allowing for a slightly dodgy axis again, is my... Now these are all straight, proper lines. Now, you should forgive my... Oh, I'm quite pleased with that. But notice how this carries on going up there somewhere. Now, 5 minus a half x. Again, this is slightly easier. I can use y equals mx plus c on this. It's going to cross at 5. And minus a half x, again, pick a number. X is 2 maybe. And you'll quickly realise that y has got to be 4. So when it's 2, it's 4. And when it's 4, it's 3. And you quickly realise it's going on that line there. I think I've kind of vaguely got it right. You often get these kind of constraints at the end as well. But before I move on to those, let's just do what it says. On both of them, it says I want it less than. I want it less than. So basically, I'm going to colour in above this line because I want less than. So I'm going to colour in, you can see, above the line. And this other line I also want less than, so I colour in the bit I don't want. So there, colour in the bit I don't want. And whatever's left over is the bit I do want. That's basically the idea. Now, what else have we got here? I haven't done these two yet. Y is bigger than or equal to 0. So I cut that one out. Look, you should know this is the line y equals 0. It's the x-axis. So I colour in the bit I don't want. I want above, I colour in the bit below it. There you go, you see? And I want x is bigger than 2. So what do? Well, this line is, line x is equal to 2. And I want bigger than it. So I colour in the bit there. And that, therefore, is my region. That's what we've got to do. Let's do a few of these. Y is less than or equal to 10 minus x. Well, that's easy enough. Y equals mx plus, minus c. And when you quickly think to yourself, if x is 10, then y is 0. So that's another one. So that actually goes through this diagonal. And these dots are very helpful for me because it means I can, with my dodgy pen here, I might have a chance of a straight line. Obviously, when you do this, you're going to try to do it really accurately. With a ruler, presumably. X is less than or equal to 7. What was 7? X, this is the x-axis. X is 7 is here. So notice I draw that line. I should start thinking about shading in. This one wanted less than or equal to, so I shade in the bit above it. What did the second one say? That said less than as well, so I shade in the bit. Now, obviously, on the x-axis, I'm shading on the right-hand side of it because it's more over here. What's the next one? X is greater than or equal to 2, so I draw the line for 2. I want more than 2, so therefore I shade less than 2. And what's the last one? Y is bigger than 0. Again, this is y equals 0. So I want more than it, so I shade in underneath it. And you quickly realise that that's my region I want. And this is what I've got to do. I've got to identify the feasible region. The last one, what's this say? It says y is less than or equal to 9. So it crosses at 9. And minus a half x, so it's going to go down. So when x, for instance, is 2, it will be on 8. And then it will be on 7. 4. That's right, yeah, I've done that. So that's my line. And I can draw a line through it. This one is 9 minus 3x. So again, it crosses at 9. Now when x is 3, I reckon it goes through there, because 3 3s are 9. So just as a matter of interest, when x is 1, I think it's going to be at 6. When x is 2, I think it's going to be 3. That's my line. And it's not perfectly straight, but you get the idea. Now, let's shade it. That one's less than, so I shade the bit I don't want. This one's more than, so I shade the bit I don't want. And this one's therefore got to be shaded underneath. What's this one? Y is bigger than or equal to 3. So y is 3 is this line here. Cuts the y-axis at 3. Whoops, does you like? Now, I want the bit greater than 3, so therefore I shade the bit which is lower than 3. And presumably these eventually will cross like that. And there's my region. So that's the first 3 done. Now, it does go a bit further than this. Now, to start off on this, you'll think it doesn't go any further at all. So I'm just going to do this one in exactly the same way. This is identify the feasible regions again. So you might want to get into this habit of doing this. So in order to find where these are slightly more complicated, what I always do is I say, well, I kind of ignore the y and I go 2 something's a 32. And obviously 2 16 to 32, so I know it's going to cross my x-axis at 16. And then I ignore the 2x and I say y is equal to 32. Oh, right, it crosses at 32 then. And that's my line. So that's my first inequality done. Next one, x and 40. Again, ignore the 2y. It crosses the x-axis at 40. That one gives me x is 40. And again, if I ignore the x and say 2y is 40, y would be 20. This one I should have written y is 32. So here I've got y is 20, and that's my inequality. If I draw it neatly, hopefully, something like that. Oh, I've also got to shade them in. They both say less than, so on both of them, I'm going to shade above the region. And they're looking very similar at the moment. Y is bigger than 0, so as we've seen before, we basically shade underneath it. That's line y equals 0 going across there, and I haven't shown you the line x equals 0 yet. That's line x equals 0. We want it to be greater, so we do the opposite. We shade underneath. No, to the left of it even. And this is my region. Now, what we're going to identify for you now is the fact that what this has done is highlight 4 regions, 4 vertices, sorry, or coordinates, where this, what we call a polygon, or for the critical feasible region. And those points, most of them you can just work out what they are quite easily. It's 0, 0. This one is 0, 20. And we've got, well, that one's going to be a bit tricky. Now, I may need to use my calculator to find that. I've obviously got an easier one here. This is 16. I knew it was 16 already. And 16, 0. But the final one, which may prove to be the important one, I'm going to use my calculator to solve. So I'm going to go into my calculator and press menu. I've got a class whiz here. I'm doing menu A and doing the simultaneous equation solver. And when I do this, 2 unknowns, what have I got? I've got 2x, I've got 1y, and I've got 32, and I've got 1x, and 2y, and 40. And it basically tells me where these 2 lines cross. Right, there it is. I've got x is equal to 8, and y equal to 16. Just look at my graph, you go, yeah, that sounds about right. So that's the 4 coordinates that we are playing around with. And what I now am meant to do is, for part C at least, I've just got one more job. It says, which of the above points maximizes the value of v equals x plus 5y? So I think of this as v equals x plus 5y, but I have values for x and y here for all my 4 points. And my job is to sub these coordinates into this, what's called an objective function, to find which one will maximize it. So let's sub these in. Where have we got? lost my pen for a moment then. So I've got 0, 0. Now if I sub these in, you'll quickly realise I get v equals 0 plus 5 times 0, which is 0. But the other ones would be more interesting. The second one, I've got 0 and 20, so it's 0 plus 5 times 20. And basically that means if I sub those points in at this point here, effectively, I get a value for v. V obviously stands for value, one assumes, is 100. The next point is, well, it's x plus 5y, so that would be 16 plus 5 times 0, which is only 16. So my winner at the moment is this point here. It's very often this one which we hear that it turns out to be the best. Now this will be, what is it, 8 plus 5 times 16. And 5 16s are 50, 80, plus the 8 is 88. Oh, well, that surprised me. Usually it's that one's the winner, but into this one's turned out that's the winner. So I think I get which of the above points the 020 does. That's the one that maximised it. We've got one more of these. So example question 2, we do exactly the same thing. Now this minus x plus y is 0. If you move the x over, you get y is greater than or equal to x. So you quickly realise this is this line going through on the perfect diagonal. Okay, now this one I'm going to say x is going to cross at 160, and using my trick from before, 120s are 180, so it's going to cross it. Now where's 120? 120 looks about there to me, and 160 looks about there. So presumably I've got down for a dodgy line. So what I've got to do, I've got to shade these in, haven't I? My first one was minus x plus y. Y was greater than or equal to x. So I want higher, so therefore I shade in underneath. That's the first one. That's the y equals x line. My second one was less than, so I want to shade that one above the line. Boom. What was this? So this says 3x plus y is 120. So my x is on 40. So it's about there somewhere. My y is on 120. Was this on 120 as well? It was. So it looks to me something like that, allowed for. And I want it to be more, so I shade in the bit I don't want, which is lower. Hopefully that's going in. And this has already been shaded underneath, so all that's gone. I think my region is here. That's the bit that's left, because that one was shaded underneath. Yeah, so that's it. And these last two are actually superfluous. X is bigger than 0 and y is bigger than 0. That's the only region I've got left. So technically I'm shading this bit here and this bit here, but that hasn't changed my region at all. Okay, so I now know my region is that. Oh, I've got to find those 2 points, I suppose. So again, I chuck these two into my calculator. I've obviously got this point 0,120. And what's my other ones? I'm going to have to solve these again. I can solve them by going menu A and simultaneous equations and 2 unknowns. And at my first equations, I'm going to do it with y equals x. So that I use the minus x, so negative 1 plus a y, 1y equals 0. And then if I type this one in first of all, so then my second equation gets 3 of those, 4 of those, and 480. And I get both of them to be 68.6. 68.6. Does that sound reasonable? Is that point there? It's a bit high. Yeah, that sounds reasonable. And the only other one I've got to do are these two. So I'm going to just go back to that and type in the second equation. So I've got the first one typed in, 3, 1, 120. And that gives me 30, 30. All right, and so that gives me a very exact point, 30, 30. Okay, so again, my v equals 4x plus y. Oh, notice this time I'm not trying to make them as big as possible. This one says minimize. Look out for that, minimize. So 4x plus y this time. So I haven't got a 0, 0 here. I've got a 0, 120. So that's 4 times 0 plus a 120. That sounds like 120. I've got a 4 times 68.6 plus a 68.6 does seem a lot bigger. I'll work it out. I get 343. Don't think that'd be exact, but close enough. It's very big. And my last one is 4 times 30 plus 30, and that's 150. So in this case, my biggest one, sorry, my smallest one this time I want, is that one there, the 120, and the 120 comes from the 0-120 point. So minimize the value. The value is actually 120. It doesn't say which point, it says minimize the value of it. So look, there's a quick run through of some basics of linear programming. Thank you.